Hello everyone. In this session I am going to show you how to solve a transmission line question. I'll take an example on a short length transmission line. We are going to calculate the ABCD parameters, the sending end voltage, sending end current and power, transmission line efficiency, and we'll draw also the phasor diagram. So let us assume we have a three-phase transmission line with a length of or let us say three-phase transmission line 100 kilometer long, with impedance per kilometer of, so we have small z of 0.032 plus j 0.35 ohms per kilometer. So this is the impedance of the line per kilometer in ohms per kilometer. And the full load, the full load at the receiving side at the receiving end side is 700 megawatt at 0.95 power factor lagging. This is similar to the example that we solved in the classroom, but the difference here, we have a lagging power factor instead of a leading power factor. So the load at the receiving side is 700 megawatt at 0.95 power factor lagging at a voltage of 3 to 7.8 kilovolt. This is the receiving end side voltage, and this is a line-to-line voltage. Even if it is not specified as a line-to-line, should be considered as a line-to-line, because in a three-phase power system we do not use the phase to neutral voltage. We normally specify the quantities in line-to-line. So this is V line-to-line at the receiving end side. So what do you want to find? Find the followings. First, A, B, C, D parameters. Of the line, and we are going to use the short length transmission line parameters. As we have only an impedance here, we don't have parallel components, we don't have capacitors or capacitance or admittance or a leakage resistance, so we are going to use the parameters for the short length lines. To find the sending end voltage Vs, sending end current Is, and the power at the sending end, and the power factor at the sending end. We need all these quantities at the sending end. And 3, we want to find the transmission line efficiency. let us say power efficiency. And what else? That's it. Maybe we can find, maybe we can add a voltage regulation if we have time. So the solution, how to solve this equation. First, for short length transmission line, we have A equal D equal 1. This actually will be also available in the formula sheet, and B also from the formula sheet equal to capital Z. But we don't have capital C, we have small z, so capital C is equal to small z times the length of the transmission line. So it's going to be 0.032 plus j 0.35 ohms per kilometer time, this is ohms per kilometer time the length of the line, which is 100 kilometer, so time 100. This is ohms per kilometer, so we multiply it by 100, the length of the line, 100. Do not multiply by 100k again. So just 100, because the unit length is per kilometer, not per meter. It's given as an ohms per kilometer, so just multiply it by 100. And this is going to give you B equal 3.2 plus, so you multiply 100 times the real number, the first number is going to be 3.2 times j 35, and you can convert this number into from rectangular form. It's a complex number. From rectangular form you can convert it into a polar form. If you set your calculator to give you the results already in polar form, then you just need to type 3.2 plus 35 I equal, it will give you the answer immediately in a polar form, which is 35.145, I would say 15. So you can round it to 2 decimals. It's fair enough. Angle, so we scroll to the right, angle 84.77, make it 0.8, okay. So for the angles, 1 decimal should be more than enough, and because this is in ohms per kilometer time kilometer, so the answer will be in ohms. Okay, so if you don't know how to set your calculator to give you the answer right away in polar form, I can show you that. So what you can do, go to Shift, Setup, then scroll down, select 3 complex, and complex results, either 1 or 2. If you select 1, it will give you always the results as a rectangular form, a plus bi, but if you select 2, the results will be always, the final results will be displayed in polar form. So that is 2, and that's it. The calculator has been set to give you the results always in polar form, and we prefer to make the results always in polar form. Because you can see, for example, here you can see it's the ohms, the effective value of the impedance, and if you have a voltage, this number for a voltage will be the effective value or RMS value of the voltage, or if this is a current, then that is going to be RMS value of the current and its angle, and it will help you to draw the phasor diagram of that quantity. So we found so far AD, which is equal 1, that's easy, and we found B, parameter B, and for C also will be given in the formula sheet for short length transmission line to be equal to 0. So these are the parameters of the transmission line. So we finished with 1, and now we are going to continue with the rest. So 2, we want to find the sending end voltage, current, and power. So what do we want here is to use the formulas for the transmission line, either in a matrix form or the one that you have learned. If you remember, we use in a matrix form VS IS. This is going to be given to you equal AB CD VR IR. So this, you will have this formula in the formula sheet. So if you open it, you can write VS equal A VR plus B IR, and IS equal C VR plus D IR. And as I told you, for these equations you have to use always phasor quantities, and also all the voltages should be phase to neutral voltages. So these formulas are for the equivalent single line diagram of the circuit. For the single line diagram or single line equivalent circuit, we use, this is the impedance and this is the load, and this is VS, and this is a neutral, and this is line. So this is the sending end side, and this is the receiving end side. Okay, that's the between the receiving side and the neutral, and this is Z, and that's going to be IS, and that is IR. So to use this formula, to use this circuit, we need to convert all the quantities given, three-phase quantities, into single-phase quantities. For example, you can find the receiving end side VR to be equal V line to line on the receiving side divided by √3. So that is going to be 327.8 divided by √3, kilovolt, and that is going to be 327.8 divided by root 3. That is going to be 189.255.3 kilovolt. This is the receiving end voltage phase to neutral or line to neutral. But we want to use this quantity as a phasor quantity, so we need an angle for this voltage, and we are going to use it as a reference. If you use it as a reference, we are going to consider its angle equal to 0. And we always prefer to use a voltage as a reference, and we choose a reference either a receiving end voltage if the quantity is already given, or if the sending end quantity is given, we can use also the sending end quantity or voltage as a reference. Next, we want to find the current, and current is not given, so we need to current. So if we want to find the voltage or the current at the sending end side, we need the receiving end voltage and current. So this is the receiving end voltage, we want the receiving end current. We already found the ABCD parameters, so we have now to concentrate on finding the receiving end current. And if we look at the given data, we can see that we have a load of 700 megawatt at 0.95 power factor lagging, so that's going to help us to find the current by using the formula for the power in the three-phase system. Three-phase P3 phase equal root 3 V line to line I line time cosine theta or time the power factor. So the power is given for the receiving end side, so all the quantities here should be on the receiving side quantities. So here the power is given to be 700 mega, so you can write 700 times 10 to the power of 6, so we convert it into watts, equal root 3 time V line to line at the receiving side is given 327.8, and you need to change this into volts. It's given in kilovolts, so time 10 to the power of 3. Then I line is the quantity that we want to find. Then time the power factor is given at the receiving end side to be 0.95 lagging, so we need just 0.95. And if you do the math, I line equal this quantity divided by all other numbers. So I'm going to write it, or what you can do in order to reduce the numbers you are punching in the calculator, you can do something. You can here eliminate 10 to the power of 3 with this, so that's going to be 3 instead of 6. It will be 3, so we can write that to be 700 times 10 to the power of 3 divided by root 3 divided by 327.8 divided by 0.95. (700) times 10 to the power of 3, you can punch immediately exp, this bottom exp, or times 10 to the power of 3 divided by, I'm going to open a bracket, and here is the thing. Here you have root 3, and you should be careful when you are punching root 3. If you punch root 3 here and you want to multiply by another number, you'll see the multiplication became under the root. So delete that. You have to multiply, you have to make the multiplication sign, the multiplication after the root. So now, so you have to click on here and bring the multiplication sign after, outside the root. And now you can punch 327.8 time 0.95. Now you can close the bracket, and that's going to be 1297.79, let's say 0.8 ampere, because we change the power into watts, the voltage into volts, the current is going to be into ampere. So the line current is 1297.8 ampere, 1297.8 ampere, which is equal to, if you want to put it in kilo ampere, 1.2978 kilo ampere. So this is the current at the receiving side, and this is the same current in the sending side. So this is the line current. The line current in the equivalent single phase circuit is the same as the line current in the three-phase circuit. For a short length transmission line, because we don't have parallel branches. So we found IR, but this is only the quantity of the current in kilo ampere. We want its angle, we want it as a phasor quantity, because these two formulas are valid only when you use the currents and voltages as a phasor quantities, magnitude and angle. So what is the angle of this current? Do we have some information that's going to tell us, if to help us to find the angle? Yes, we have the power factor is lagging. So we can, if you draw the phasor diagram of VR, this is the VR receiving end side, and lagging, so the current is lagging, IR lags the receiving end side by an angle, that is cosine inverse power factor. Put plus minus. Use minus, negative sign, if the power factor is lagging. When we say power factor is lagging, we means current lags the voltage. So we are going to select negative sign, not positive sign. If the power factor is leading, then we are going to use positive sign. So the sign we are going to use is the negative sign, and that is in kiloampere. So IR receiving is 1.2978. Negative cosine inverse, power factor is 0.95. It's different than the example we saw. In the example it was 0.99 leading, this is lagging. So IR is 1.2978, and this is in kiloampere with an angle of, let us see how much cosine inverse, shift cosine inverse 0.95 is how much, 18.19, and for the angles it's okay to use just one decimal, 18.2 degrees, and again that is in kiloampere. Make sure always make sure that the angle you are using in degrees, not in radians. So that should be, I think, available on the setup. Shift setup 3. Okay, so you have different modes of angle: degrees, radians, and grade. So 3 is the angle. You should have the letter T, and that is telling us this setup is for angles and degrees. So this is IR, and now we can find VS, we can find IS, because we now have all the quantities on the right hand side, and we can find VS equal A, which is 1, so 1 time VR plus B time IR. So 1 time VR is VR plus B, which is capital Z, this is B equal capital Z, time IR, and VS equal VR. So VR is, see, use VR phase to neutral, again be careful, 189.3, angle 0, you can ignore angle 0, and this quantity in kilovolt. So I am not going to write kilovolt, I can write it at the end. So this is quantity in kilovolt. Because this is quantity in kilovolt, be careful, you should have the other term in kilovolt also. And the other term will be in kilovolt if you have IR in kiloampere. This is why I converted IR into kiloampere here, because we have Z in ohms. So when you multiply ohms by kiloampere, you will have kilovolt. So I am going to use Z, which I converted here in polar form, which is 35.15, angle 84.8. This is ohm, time the current IR in kiloampere is this one, 1.2978, angle negative 18.2 degrees, and close the bracket. Now we can find VS using the calculator in complex mode. So what I am going to do, I am going to punch this number without the angle 0, so just ignore it, and that is 189.3 plus, open bracket, 35.15, shift angle 84.8, close the bracket, multiply by the other number between brackets. So you can punch this multiplication sign, or you can just ignore it if you have just brackets beside each other. So you have two numbers between brackets is going to be multiplied by each other automatically. 1.2978 angle negative 18.2. For negative, do not use this negative sign, use this one. Negative 18.2. Close the bracket. When you hit equal, you will have the answer immediately right away in a polar form. So because we set the calculator to give you the answer in polar form. So 211.599, so 211.6 angle, scroll to the right, and we use two decimals for the angle 11.4 degrees. And the answer, again, as I told you, it will be in kilovolt, because this is quantity kilovolt, and this quantity is in kilovolt because Z in ohm, I are in kiloampere. So both quantities are in kilovolt, because you cannot add kilovolt to volt. It should be two quantities should carry the same units, kilovolt plus kilovolt. So the final answer will be in kilovolt. So we have Vs, we obtained Vs, and we can, if you okay to draw the phasor diagram just right away. VR is a reference with angle 0, and IR with angle of negative 18, so it should be down. That is negative 18.2 degrees, and that one is now leading, and leading the reference, so it says an angle of 11.4 degrees Vs. And we should actually make it a little bit longer, because it is more than, if you compare it to VR is 189. So maybe to have good phasor diagram, you need to make it longer than VR. So this is Vs. No need to worry about how much longer it should be, because just an estimation. Okay, so you want to be reasonable, no need to be precise in the length of the phasor. Even for the angles, just be reasonable, for for the angles. Okay, so we found Vs. Next we need to calculate Is. You do the same thing. Is, we have the formula for Is, equals C times VR, and C is equal 0. C is 0, so 0 times VR is 0, plus D times IR, and D equal 1, so just 0 plus IR. Or you can immediately say Is equal IR for short length transmission line, and that is the same quantity, which is 1.2978 angle minus 18.2 degrees kiloampere. So for Is, you just simply put Is equal IR, but you need to show me the quantity. It's not enough to just write Is equal IR. You just put the quantity is 1.2978 angle minus 18.2 degrees, and show me the units in kiloampere. So IR and Is, actually they are on top of each other. They are same magnitude, same angle. This is IR and Is at the same time. So it's enough to do this for short length transmission line, but for long length or medium length transmission line, we need to show this with detailed calculations. So we're done with IS. Now PS, let us do the power factor first. It's easier to measure the power factor at the sending end side. PF sub S, power factor at the sending end side. The power factor is, the definition of power factor is the cosine of the angle between the voltage and the current. The voltage at the sending side minus, let us say the current, the angle, theta, so we should put theta, sub Vs and theta sub Is. So the angle between the voltage Vs and Is. Do you see this angle? This is Vs, this is Is. How much the angle is going to be added? So you can either say power factor S is equal cosine the total angle, this angle 11.4 plus 18.2, this big angle, the current between the angle between the voltage at the sending side and the angle at the current, the angle of the current at the sending side. So these angles are going to be added together. That's going to be cosine of 11.4 plus 18.2. That is 29.6. Or if you want to use this formula, so PF of S equal cosine, what is the angle of the sending side is 11.4 minus the angle of the current at the sending side is minus 18. So put another bracket, minus 18.2, and that is going to be cosine 11.4 minus is a plus 18.2, and that is going to be cosine 29.6. So same thing. And cosine answer, which is 29.6, is 0.869. Let us round it to 3 decimals. 0.869. But you have to tell me, it's not enough to tell me that the power factor is this. Always with power factor, one word should be associated, another word, either lag or lead. As you can see, the current IS is lagging the voltage Vs. So IS lags Vs, so we say lag. So power factor at the sending side is 0.869 lag. Now we can calculate the power 3-phase at the sending side using the famous well-known formula for the power in a 3-phase power system, √3 V line to line, I line cosine theta, or power factor. All these quantities should be sending end quantities. We have the line current, we found it. This is the line current, which is the same of the sending and receiving side current. We found the power factor, but we need to use the line to line at the sending side. So the voltage at the sending side, which is also required, we should find the voltage before the power, but no problem, we can do it now. We have, this is the magnitude of the phase to neutral voltage. So line to line is √3 times line to neutral at the sending side. So that is √3 times, see, this is why we use a polar form. Polar form will give you the magnitude, so we need to multiply this by the magnitude to 11.6, and don't forget this is in kilovolt, and the answer will be also in kilovolt. So again, if you multiply root 3 times this number, you put the multiplication sign outside the root, time to 11.6. That is 366.5 kilovolt. This is the line-to-line voltage at the sending side, which is more than the receiving side voltage, but that is normal because of the voltage drop. So if you apply this formula, you can say power at the sending side is equal root 3 times line to line is 366.5. This is in kilovolt, so I'm going to write kilovolt here, and I will tell you why later. I line is in kiloampere, which is 1.2978 in kiloampere, and the power factor is 0.869, and when you multiply kilovolt by kiloampere, the answer will be in mega. So that is going to be root 3. You can do this for root 3 and close the bracket outside the root, open another bracket for the voltage 366.5, and open another bracket for the current 1.2978, and open another bracket for the power factor 0.869, and just want to make sure 0.869, yes, equal to 715.9.92 megawatt, because K times K is megawatt, and that number should be more than the receiving side. So the sending side was 700 megawatt, this number is 715 megawatt, that 715.92, that means we have a losses of around 16 megawatt, 15.92 megawatt. So this is the three-phase power at the sending side. And finally, transmission line power efficiency. This is the third requirement. The efficiency is defined as the power at the receiving side, which is the useful power that we can use, divided by the total power at the sending side times 100%, and that is going to be 700 divided by 715.92 times 100%, and that is going to be 700 divided by 715.92 times 100. So the power efficiency is 97.8%. That's all what is required. And if you want to calculate the voltage regulation, which is not required in this example, you can do the same thing that we have done for the voltage regulation calculations in the example given to you. Okay guys, so we have finished today for this example, and I hope for you good luck in your quiz next week. Bye.